Just have something. Just have and I just tell you. Okay. Great. Yeah. Holy cow.
Like advertise this too well.
This is Louise back here, but you got plenty of space. And for the people who don't have space, there's also Zoom, and Thomas is here. So you can always just ask me questions. Yeah, this is going to be like, this is a weird talk. Like, I'm talking about stuff that is like very, very sort of very theoretical right now. So, you got a good audience for this seat here.
Are there's okay. I was like, are those open?
Once Jessica gets in, let's get started. Good little online crowd too. It's great. Right, I think I've got it within like the 45 minutes, but you know, I start to go too long, just like wave or
Yeah.
know.
It will be nice to have some Q and A after. So
Yeah.
So I'll give you like a little 5 minutes.
Yeah, there's a certain amount of sort of information theory background that I kind of have to build, and that needs more
I
time.
think that's for this crew, that's gonna be perfect.
Okay.
So I'll just keep introductions quick. This is Dr. Thomas Varley. Thomas is a researcher at the University of Vermont. Does PhD at Indiana University, and for years has been sort of a Twitter buddy, basically, but also like scientific, both shadow collaborator. We've never actually done anything together, but I get a lot of Thomas's work. And then collaborator.
Yeah.
So please take it away.
All right. So, yes, thank you for having me, Brennan. It's really cool to get to visit Northeastern. I've always wanted to come out here. And I'm going to be talking today about some work that is, this is sort of its first primetime showing, essentially. Some of these ideas are a little bit odd, some of them are a little bit out there, and so I'm really curious in the Q&A session if I could get some feedback from you guys. Does this seem interesting? Does this seem believable? Does it seem insane? Not many other human beings have kind of seen this line of work. So I'm going to talk about this idea of dark information, and I'm not going to be able to move my mouse forward. There we go. Okay, so I'm really drawing on an analogy here with dark matter and cosmology. And I want to preface this by saying I am not a cosmologist, so this is sort of based on my pop science understanding of cosmology and dark matter, and I'm sort of leveraging that for this idea of dark information. And so to make this analogy a little bit more formal, in dark matter, when we're talking about dark matter, it's this stuff. It forms the vast majority of the material in the physical universe, as far as we know. We don't really have any good technological or even theoretical frameworks for interacting with it. We know it's there, but we can't really interface with it. And it doesn't really fit with the existing very successful models of physics. And then so when I talk about dark information, I'm talking about information or statistical structure in a complex system that potentially forms the vast majority of the statistical stuff as opposed to the material stuff that describes the system, okay? And again, we currently don't have very many tools to directly observe this information or interact with it, and it doesn't fit very well with existing successful data science approaches for analyzing complex systems. Okay, so if you believe me that this dark information exists, which hopefully by the end I will have convinced you, you will maybe see where this analogy is kind of coming from. And so what is dark information? How do I formalize this mathematically? And so coming out of my PhD, I had this idea of dark information as a fancy way of talking about, higher order interactions in complex systems, and particularly a kind of higher order interaction that is called synergy. Okay, this is information that is present in the joint state of multiple elements of a system, but not learnable when you consider any subset of elements. It's the information that is in the whole that is not in any of the simpler parts. Okay, and so to kind of bring you all up to speed, I'm going to blaze through a hopefully very painless tutorial on discrete information theory and then multivariate information theory. You all are PhDs in complex systems or related fields, so I'm hoping you're at least familiar with the basic concepts like entropy. But for those of you who are not, the basic object of study in information theory is the entropy, and you can think of it as a measure of either your uncertainty about the state of a random variable. If you flip a coin, how much do you believe that it is heads? How much do you believe that it is tails? Or alternately and equivalently, you could think of it as a measure of, how much work do I have to do in the form of asking questions to specify the state of the coin, right? So whether you want to think about it as sort of a pile of uncertainty or, an amount of work that has to be done, those are mathematically equivalent. But you can think of it as a way of quantifying your beliefs as an observer about, the structure of the system that you're studying. And it's really important that we're talking about your beliefs here, okay? Once you have entropy, you can start to build more complicated measures. So the basic interaction between two variables is the mutual information. And you can think of this as the difference between your initial uncertainty about the state of, x1, and then you subtract off the uncertainty about x1 that remains after you have learned x2. Okay, so the difference between your prior uncertainty and your posterior uncertainty is the uncertainty about x1 that is resolved by learning x2. Okay, and mutual information is symmetric in its arguments. You could do the same thing with x2 and the conditional entropy x2 given x1. Okay, so far so good? Everyone hanging on for dear life? Cool. And then importantly, if x1 and x2 are independent, then the mutual information is 0 bits. So that's the only time the mutual information is 0 bits, okay, is when they're independent. So you can think of mutual information as kind of a fancy correlation. If you're familiar with the Pearson correlation, mutual information is very, very similar. And so, most neuroscientists and biologists just kind of stop here. You take your favorite system, you parcellate it into parts, you extract some data, and then you form a pairwise mutual information or covariance matrix that defines the adjacency matrix of a graph, and you're off to the races. You can do motifs and modularity and whatever you want, in your network science toolkits, okay? Always just stopping at the pairwise mutual information, okay? And so kind of riffing on Laszlo here, pairwise mutual information is all you need. Maybe you're too young to get that reference.
They actually, I think, are too young.
They are. That makes me feel really old.
2018.
Yeah. And so, does this always work? And no, it doesn't always work. No tool is universally successful. And I'm going to walk you guys through a case study where this approach fails spectacularly. And that will hopefully motivate the need for all the higher order stuff coming. So let's imagine that you're a scientist and you're observing this system. Okay, every frame you look at it and you see that it's got 3 elements. They can be on, they can be off, and every time you look, they're in some different configuration. Does anybody recognize the system? Computer science people? Going once, going twice. Okay, it will be revealed at some point. But so you watch this system, you collect some data like a good empiricist, and you form this lookup table. Okay, you say, okay, this looks kind of like a finite state machine. There's a quarter of the time it's in 0, 0, 0, a quarter of the time it's in 0, 1, 1. How should you model this system? Okay. And, all being PhDs in network science, your instinct might be, okay, well, let's look at the pairwise interactions between x1 and x2 and x3. What will your network look like? Anybody have any guesses? Dina?
Oh, sorry. The pairwise?
No. Your network will be completely empty. The correlation between any pair of elements is 0 bits. You do not have a network of any sort. You have 3 disconnected points just floating in space, not interacting with each other in any way. And so you might say, well, maybe this isn't a system. This is just like an ideal gas of things turning on and off at random, and there's no statistical structure. But if you actually look at a random distribution on a set of 3 binary variables, it's a very different distribution. Okay, this Q is the true maximum entropy random distribution, and this is P, this is our data distribution that we collected by observing the system. And if you look at the Kullback-Leibler divergence between these 2 distributions, you don't have to know what the Kullback-Leibler divergence is. All you have to know is that 1 bit of information is present. So the system is not random. It is not an ideal gas. There is information in it, but it is not in any of the pairwise interactions. So where is it? Where is this information? Where is its structure? How is it deviating from independence? And the answer is this information is encoded in the joint state of multiple variables. And so you always have to know at least two to resolve the third. So I showed earlier that the pairwise mutual informations are all zero. But then if you look at the mutual information that the joint state of x2 and x3 discloses about x1 and x2 disclose about x3, suddenly you have one bit. One bit of information has appeared seemingly from nowhere when you start looking at higher order interactions between elements. Okay? So knowing the state of any pair of elements automatically resolves all uncertainty about the state of the system, but knowing any single pair or any single one resolves no uncertainty. Okay, and so when we talk about synergy, this is what we mean. And so, if we want to move past the sort of this toy model example of logical XOR gates, what we need a formal logic that can sort of rigorously describe, in the most general case, interactions between three or more elements without reducing them to combinations of lower order interactions. And so I'm kind of coming here to a network science department and saying, the networks are broken. We need something that can go beyond that. And so this brings us to my favorite topic of conversation, multivariate information theory. Before I start, anybody have any questions about this? Motivation seems believable. XOR gates, cool. Okay, so we're going to leave the world of pairwise mutual information behind. We are going to enter this world of higher order informative interactions, and we are going to immediately hit a brick wall. And that brick wall is that if you have three or more variables, there's actually different kinds of correlation that can exist. This is not something we typically think about in the pairwise case. A correlation is a correlation is a correlation. But if you have three or more elements, correlations can suddenly start coming in different flavors. Okay, and the two flavors are redundancy, which is information that could be learned by observing x1 alone, or x2 alone, or xn alone. And then there's synergy, which is information that can only be learned when you observe x1 and x2 and all xn together. Okay? You can also mix and match these to your heart's content. So you could have the information that you could learn by observing x1 and x2, or x1 and x3, or x2 and x3. And so if you sort of think about the combinatorics of this as the system gets larger, it becomes really, really, really difficult to brute force. And so, to think about what these sort of flavors are, I like to use two examples. So for redundancy, it's this wonderful photo of these North Korean soldiers marching. And if you know what, leg position any one of those soldiers is in, you automatically know what leg position all of the soldiers are in, right? You only have to observe one, and then the whole system becomes completely transparent, okay? And so we associate redundancy with synchrony. If you have a system where everything is highly synchronized, if the metronomes are all ticking in time together, that's a system dominated by redundancy. Synergy is kind of harder to grok in a sense, beyond saying that it's XOR like. But my go-to analogy is something like a symphony, right? In a symphony, every individual instrument is playing a different piece of music. But those pieces are related to each other, and so the whole experience of listening to the symphony is in some sense sort of greater than the sum of its parts. If you were to listen to just the tuba section of the symphony, it probably wouldn't be that interesting. If you were listening to just the string section, it probably wouldn't be as interesting. But when you get all of them playing together, there is stuff happening that is not reducible to any one part on its own. Okay? And my hypothesis then is that almost all of the popular tools in neuroscience, and by extension other complex systems fields, are preferentially sensitive to redundancy and functionally blind to synergies. And so I was talking to a guy at the Santa Fe Institute who gave me this really great quote. I forgot his name, so I can't credit him. But he said that, existing tools, it's like they just ask, is everybody jumping at the same time? You look at those ballerinas and you say, are they jumping? But what we really want to understand is, are they dancing? Is there, some kind of structure to their interactions that is beyond just, how many of them are up in the air at one time? What is this sort of emergent quality that defines, a really nice piece of dance? And so that's, what I'm going to be trying to build we're still in the introduction to the talk, but, over the next couple of slides. Okay? Everybody get the distinction between dancing, jumping, redundancy, and synergy? Okay. So there is a small but growing literature on quantifying, higher order information, trying to find tools that are sensitive to dancing and not just jumping. There's various partial information decompositions. There's an alpha synergy decomposition, synergistic disclosure, and, you know, um, all of these citations sort of defined the reading that I did during my PhD. And the one that I'm really going to talk about is extensions of multivariate mutual information. It's the most accessible, and also it sort of scales the best when thinking about larger systems. And so we're introducing another measure, and this is specifically a measure that takes the basic idea of that pairwise mutual information and extends it to the case of arbitrary numbers of variables. Okay, so we call this the total correlation. And it quantifies the degree to which a given system is more structured than you would expect if all of its elements were behaving independently. Okay, so just like the mutual information, if every element is independent of its complement, then the total correlation is zero. I said before, if x1 is independent of x2, mutual information is zero. This is just the higher order generalization of that identity. And so you can think of the total correlation as quantifying something like how different is your system from an ideal gas. If it's an ideal gas, all the molecules are just bouncing around randomly, total correlation will be zero. If your system is structured, deviating from independence in interesting ways, the total correlation will be large and non-zero. Okay? And so the last piece of mathematical heavy lifting that we're going to have to do is we're then going to have to take the total correlation and build it into a measure called the O information. Okay. And the O information is a summary statistic that measures specifically the higher order deviation from independence and whether that deviation is redundancy dominated or synergy dominated. And so if you feed a variable into the O information and it comes back as greater than zero, then you know that the structure of that variable is redundancy dominated. It looks like it is synchronous in some way. It's like the North Korean marchers. In contrast, if you feed a variable into the O information and it comes back negative, then that system is synergy dominated. It is more like the orchestra or the dancers than it is like the North Korean marchers. Okay. And importantly, the O information inherits the same property as the total correlation, that if all of the elements are independent of each other, then the O information is zero. Okay. And so that means that a non-zero O information is sufficient to show that your system has higher order structure and deviates from independence. Okay. If I show you a random system, its O information should be zero. Okay. And that's going to be important later because we'll see that there are other tools that cannot distinguish between truly random systems and systems that have negative O information. Okay. So O of zero is sort of a stricter test of randomness than something like not having any functional connectivity or network structure. How am I doing on time, Brad?
Great.
Great. Okay. Okay. And then so, you might be asking, does any of this actually matter to real scientists? If you're Mike Levin in a lab looking at a xenobot, does this mean anything to you? Or am I just playing a mathematical shell game with XOR gates because I'm a mathematician and like playing mathematical shell games? Well, yes. And what I'm going to do now is sort of transition into a case study where I'm looking at fMRI data specifically. This is data taken from one person, scanned 4 times. And what I'm going to show is that if you take this Humming, that's an interesting typo. If you take, sort of the existing popular techniques in neuroscience, which in this case are functional connectivity, network analysis, and manifold learning analyses, that those techniques will fail to disambiguate between random systems and synergistic systems. And moreover, that those same techniques tend to be overly sensitive to higher order redundancies, as well as being blind to the synergies. So for those of you who don't care about neuroscience, you can just tune out, but this is 4,400 TRs. One person as part of the Human Connectome project scanned twice. We parcellated the cortex into 200 brain regions, and we computed O information and a bunch of other measures that I'm not going to talk about, specifically using non-parametric information estimators. Okay, so you might say, well, maybe this is just a weird quirk of discrete information theory, or maybe you used a Gaussian estimator and this is a weird quirk of joint normal distributions. We used the most sort of conservative, non-parametric, no assumptions required, computationally exhaustive way of inferring these measures, making no distributional assumptions of any sort, or discretizing the data. And so what I did was I computed the triadic O information for all 1.4 million sets of 3 brain regions, and then compared the functional connectivity structure of those triads, the PCA-based manifolds learning structure of those triads, and the O information of those triads. And so starting with the network approach, a couple of things jump out immediately. All right, so we took the functional connectivity network, used a multi-resolution consensus clustering algorithm to group it into communities. And then we looked at, okay, how are redundancy-dominated and synergy-dominated triads distributed over the community structure? Okay, and so up here, you can see that, dark red is all triads that had, 1 foot in 3 different communities. Slightly paler red are triads that had 1 foot in one community and then 2 feet in another community, so split pairwise. And then the palest color is all the triads that sat within one community. All right. And so the first thing that you see is that almost no redundancy dominated triads spanned 3 communities. The triads that all sat within one community or spanned 2 communities, they were the vast majority of the redundancy dominated triads. Okay. And you see the opposite effect in synergy. Okay. For those triads that are synergy dominated, almost none of them all sit within one community. Okay. And most of the synergy dominated triads, the strongest, most synergistic triads, they are the ones that had 1 foot in each of the 3 different communities. So if your approach is to take the network and to do the community detection, what you're really seeing are redundantly integrated communities. This higher order synergy, it's kind of in this, in these hollow spaces of the network that are not, don't fall onto this nice map that you get when you do modularity maximization analysis or something like that. If you also just look at the average pairwise mutual information between the 3 elements of the triad, and you split it by redundancy dominated or synergy dominated triads, you can see that the average mutual information, is much, much lower for the blue synergy dominated triads than for the redundancy dominated triads. And so when we put all of this together, my argument is then that the functional connectivity network analysis is showing you a biased picture of the information distributed over the data set. Okay, what you're really seeing is the redundant information, particularly seeing higher order redundant information that is being projected down onto the pairwise functional correlations. And the synergistic information, again, is sort of off in the hollow empty spaces that the network analysis doesn't sort of ascribe any significance to. Hopefully, oh yeah, question?
Does that mean that the total entropy of the sort of triads, is it lower for the blue than the red? Or
typically higher for the blue. And I can explain for math reasons why that has to be.
Okay.
Yeah.
So, okay, so in my previous history of whatever whatever I was doing, so I had a similar project where I was using interaction information between stock times series data. And that there was a similar observation that all these synergistically dominated triads were belonging to different sectors of stocks, because naturally what you observe is that stocks belong to the same sector are in the same community. So more or less the same results, right? That the synergistically dominated triads belong to different communities. And my sort of question is this, right? That really what the O information for 3 number of random variables is this interaction information is the difference between the redundancy and the synergy, more or less.
Yes.
Right. So what usually happens is that the reason then you might be observing that is just because there is less redundancy between or less pairwise correlation between things that are in different communities. So the synergy suddenly sort of is shown, more or less.
So that's a really good question. If the 3 stocks or the 3 brain regions were just independent, they were just not doing anything together, then the O information would be 0. Okay. So the fact that they are showing statistically significant synergy does suggest that there is some kind of interaction. They are deviating from independence in some way. Whether it's the redundancy is masking the synergy, and kind of when you get rid of the redundancy, the synergy can shine through, or whether they're on equal footing, I don't think we have a great sort of heuristic sense of that yet.
Yeah, for example, in the redundant triads, right, it might just be the case that the pairwise correlations or the redundancy is so much higher that it is actually masking synergy, even though there might be synergy between three entities that belong to the same community, for example.
Yeah, so I didn't really articulate this perhaps as well I should have. O information does only tell you about redundancy or synergy dominance. Just because you have a positive O information doesn't mean that there is no synergy, just that the redundancy swaps. And like what the opposite is also true. If you have a negative O information, there can still be redundancy. It just means that the synergy swamps. That's sort of why I said it's more like the symphony than the marching soldiers, but a symphony does have some redundancy in it. All the violin chairs are playing the same motif, for instance. I have done some work on trying to untangle those two, and I can talk about that afterwards, because that turns out to be a really, really hard problem. Okay, so then if we look at the manifold learning approach, which is sort of the other big popular thing in computational neuroscience, we see basically the same relationship, okay? And so on the y-axis, we have the variance explained by the first principal component, okay? So you can think of this as a measure of how compressible is your system, okay? How much of the variance can you squeeze down onto just one dimension? And then on the x-axis, we have, this is the O information, just with a slightly different notation. And then again, we split it by redundancy and synergy dominant triads. And what you can see is that both of these are very strong, really significant positive correlations. It's not often that you get a row of like 0.95, unless something like analytically has to be the case. And in both cases, what you can see is that as the O information gets more positive, so as you drift to the right, the compressibility of the system increases. And this is true both for the redundancy dominated and synergy dominated triads. And if you look specifically at the synergy dominated triads, the theoretical lower bound on variance explained by the first principal component in a random system is 33%, right? If the system is completely disintegrated, you just can parcellate variance over to the components uniformly. And a sizable number of those synergy dominated triads are pushing this 33% lower bound, all right? And so the PCA is looking at this data, which we know is not random because it has this negative O information, that is saying I cannot parcellate the variance out in any sensible way. I'm just putting a third of it on each component. Okay, and again, if we look at the proportion of variance explained, just sort of projecting these down onto a histogram, again, significantly very different. The redundant triads can always have more variance explained than the synergistic triads. Okay, so synergy has this very interesting property that it is incompressible in the way that a random system is, that it remains, but it's still deviating from independence. It appears random, but it is still structured. Okay, and so that's just sort of reiterating everything I just told you, that the functional networks fail to capture synergistic structure because they typically prioritize redundantly integrated sets of nodes. Synergistic dominated triads sit between communities in what I'm calling these hollow spaces, and the pairwise mutual information density correlates with redundancy and not synergy. Similarly, manifolds, everything I just said, the more compressible the triad is, the more redundancy dominated it is. Synergy is sort of incompressible and appears random to the PCA. And then so sort of looking forward to, what does all of this mean for us as scientists who are interested in analyzing complex systems? There is some emerging evidence that synergy isn't just sort of mathematically interesting, but that it is also important for things that we care about. And again, my background is in neuroscience, that's where most of my examples come from, but I can tell you there are other examples in economics and climate data and all of that. We know that synergistic information is decreased when consciousness is lost. So if you hit somebody on the head and they lapse into a coma, the synergistic information that their brain is producing typically decreases. Conversely, the amount of synergistic information in an infant brain later predicts cognitive scores. So you can see how much synergy is in the EEG data of a baby in the NICU. You can predict that baby will have better performance on reading and math scores 1 to 2 years later. That's a pretty new results that I got with some collaborators in Finland. Psychedelic drugs seem to change the balance of higher order information in neural cultures and in neural networks. For people who are interested in AI, synergy in particular neurons seems to facilitate multimodal processing in artificial neural networks. And there are, more of these papers are published every day. So it seems like synergy isn't, again, it's not just an interesting mathematical shell game, but it's telling us something really interesting about how systems integrate information, how they learn, how they combine streams of information into something useful. And then finally, I kind of want to return to this idea of dark information, because when I talk about dark matter, I mentioned that it's most of the stuff in the universe. And that was sort of, I think, the last point that I wanted to make about the dark information, is that as your system gets larger, the number of possible higher order dependencies expands vastly, vastly faster than the number of possible pairwise dependencies, right? We're all familiar with the formula. You've got n squared minus n possible directed dependencies for n elements, right? So for 200 brain regions, that's something like 19,900 possible edges. Undirected edges. I'm using directed and undirected here more loosely than I should. But if you look at that same 200 set of brain regions, but look instead at five-way interactions, so the pentuple synergy, there's, what is that, like 2.5 billion possible interactions. And so, we have really just like scratched the surface of like the possible structures that can be observed and learned about, even in the most well-studied systems like human fMRI data. And so I'm going to end here, forgive me, by getting a little bit romantic. And saying, I sort of have this image, of like, we're kind of splashing around in like the waves of, complex system science, learning about these very simple, combinations of one, maybe two, maybe three, if you're really working hard, neurons. But then there's like this whole universe of, 100th order interactions. And I have no idea if any of that contains useful information, but neither does anybody else. So it'd be pretty cool to sort of strike out from shore and see, what's out there in the deep reaches of the synergistic dark shadow structure. All right. And so that brings me to the end. I want to thank Dr. Olaf Sporns, who is my PhD mentor, very soon to be Dr. Maria Pope, who's still in Olaf's lab. She's defending in like a couple of weeks. And then Josh Bongard at UVM, who is my current PI. The Cold Regions Research and Engineering Laboratory up in Hanover cuts my paychecks, and I am mostly affiliated with the Vermont Complex Systems Institute up at the University of Vermont. So thank you guys for listening, and I'm happy to talk about any of this.
That was great, Thomas. Thank you. So this is perfect. We have time for a bunch of questions, both in person, and I can also field online questions as well. And yeah, okay. Yeah.
Maybe I can try again with my question from before. I was just trying to like suss out intuition of like, is it just that redundancy is a stronger signal? But like, is it that the redundancy triads just like have more like there's lower entropy for them, so there's just like more to pick up on from the basic pairwise stuff, or is it not that?
It's a little bit more complicated
Okay.
than that. So imagine that you have a triple Venn diagram. Okay.
Yeah.
The redundancy is going to be that information that's in the triple intersection. Okay.
Mhm.
And then if you look then at the double intersections of each, there's going to be 3 double intersections. The redundancy will contribute to all 3 of those double intersections. So if you treat your system as a network, just looking at double intersections, that triple intersection is going to be triple counted. It's going to make a contribution to all of the pairwise dependencies, that it participates in essentially. And so as the order of your redundancy increases, it's touching more and more elements. And so it's getting double counted, triple counted, quadruple counted more and more times.
I see.
And so there's a sense in which it is easier to see redundancy because any single element you look at will have a little part of it. Whereas synergy, you can see it only when you observe the whole system, and it falls apart as soon as you try to like break it down into anything simpler.
And that's like controlling for whatever entropy of the joint distribution of the entire triad, or 4 or 5.
Yes, it's actually very hard to control for the joint entropy or the total mutual information. That's an area of active research.
Okay, cool.
The redundancy and synergy are not, I'm sort of talking about them as if they are independent, sort of pools of information. They're not truly independent because of something called a free distributive lattice and a Mobius inversion, and I can't go into that right now, but you can kind of, the way we think about synergies, it's kind of like all the stuff that's left over when the redundancy is partialed out. And so yes, the amount of redundancy will influence how much synergy is kind of left over because the way you compute them, they're like reciprocals of each other. But again, this gets into some more complicated math that I can talk about, things like a whiteboard and a pen and paper and stuff like that.
What are the heat maps if you were to do like one-on-one axis?
Typically very highly correlated. Systems that have lots, I think, although again, this depends a lot. So right now, when I talk about the O information, I'm using redundancy or synergy dominated. If you pull them apart, there's no unique way to do that. There are a lot of different ways, and it depends on how you define redundancy. But in general, the most popular ways of pulling them apart, redundancy and synergy are typically correlated. So, systems are either independent or redundancy and synergy dominated with, or no, either independent or strongly integrated with both redundancy and synergy. It's actually quite rare to see a system that is like all one or all the other. I kind of have to construct it artificially with like copy gates and XOR gates and things like that.
Get back to the chat. Oh,
So there's a question.
um, so, Java from the chat says, what would be some extreme cases where the system is almost fully synergistic or redundant?
So any system that is, sorry, who was that question?
Java, so
Oh, okay. So any system that is synchronized will be highly synergy dominated or redundancy dominated. Just like those North Korean soldiers. It's very hard to find an equivalently intuitive synergy dominated system. The logical XOR gate for discrete binary systems is synergy dominated, and it's kind of the only one that we've found. If you are looking at Gaussian systems, like vector autoregressive processes, systems where the primary frequency of each element, if those frequencies are co-prime, those systems are synergy dominated, and I don't think anybody has a great idea as to why that is. And I think I'm articulating that correctly. But yes, there isn't anything as obvious as synchrony equals redundancy for synergy. I will say that I have a paper in MDPI entropy that came out earlier this year showing that synergy occurs anytime you have a causal collider. So for any of you who are interested in like causal inference, whenever you have a collider motif, you're going to get almost always going to get a synergy dominated system. So one of the reasons I think synergy is so interesting is it could be kind of a fingerprint of colliders integrating information somehow. But that's not very intuitive to say, oh, there's probably colliders under the hood. Doesn't hit you the same way as I would synchronize.
So I have two questions. So I completely agree that when we are talking about O information, we are talking about the dominance of either the synergy or redundancy, right? And you mentioned that there is no like agreed upon definition of redundancy that is used in the literature.
Yeah.
But so what is the more or less the agreed upon version?
So this gets into this is a complicated, controversial thing. If you want to fully untangle all orders of redundancy and synergy, you're going to use something called a partial information decomposition. The partial information decomposition requires defining a redundancy function. And if you define redundancy function correctly, you get everything else for free. You get the free distributive lattice, the Mobius inversion is valid, and you can get everything that you want. Unfortunately, there are many functions that satisfy the original axioms to produce the free distributive lattice. And there's not really an obvious way to narrow it down beyond that, except, I have my favorite redundancy function. I happen to have my favorite redundancy function. I think Connor Finn and Joe Lizier pretty much hit the ball out of the park with their localizable approach, but it's everybody wanted something like Shannon's entropy. Shannon said, here are my axioms, and then he proved that the entropy was the only function that satisfied all of those axioms. We wanted that for redundancy. We didn't get it. And so now you kind of just see which one is most appropriate for the study you want. Different redundancies capture different intuitions. And so maybe There's some contexts in which, Finin-Lizier's localizable measure makes more sense, or there's other functions where Bertshinger's Brosia measure makes more sense. There's not a uniquely specified measure.
One more thing, sorry. So you mentioned non-parametric estimators.
Yes.
So do you have any references for those? Or
Yes, these are all based off of the Kraskov mutual information. Under the hood, the intuition is sort of like, imagine you have some weird probability distribution, non-parametric, strange, high regions and low regions. If you sample points randomly from that distribution, the points from the high maximally likely areas will be densely close to each other, and points sampled from the low probability regions will be far apart. So then if you compute then the distance of every point to its kth nearest neighbor, you can kind of backdoor your way into an estimate of the local probability density around that point. Points where the nearest neighbor is very close come from high probability regions of the manifolds. Points that are far away from any neighbors are from low probability regions. So from that intuition, you can bootstrap a whole family of measures. Kraskov mutual information, you Google that and you will I should shout out, I didn't include him on the acknowledgement, but I should shout out Pedro Mediano, who is somewhere in the UK right now, I think UCL. He wrote some of the backend code for the non-parametric O information, and that's part of the JIDT package from Joe Lizier.
That we use.
Yes, I'm currently in the process of putting the finishing touches on my own package, which will be called Syntropy, and that's all pure Python, no futzing around with Java docs. That will be hopefully hitting GitHub in the next 2 months. But for now, yes, JIDT is my go-to, or IDTXL if I'm doing transfer entropy.
Maria has a question in the chat.
Oh,
Maria and Sarah.
Maria, do you want to just turn on your camera or you can read this loud? I think
Let's try to, Maria, if you can hear us, could you turn on your mic? Actually, work as well as I thought it would.
Oh wait, Maria, say something. Oh, whoa, that's weird. Nope.
Yeah, let me do on this one. All right, can you try something?
Okay. I guess we can just read it aloud.
She said, "Mike's not working out," but
Okay.
yeah, let's read it.
So the way you explained the overcounting of redundant higher order interactions was great. Thank you. But made me wonder, is there any way to distinguish between truly higher order redundancies versus lower order redundancies? If you assume that the higher order redundancy exists, then they will be overcounted. But what if the collection of pairwise redundancies makes it look like there is higher order redundancy? Because higher order redundancy will always be counted in lower order terms, does the distinction, oh boy, that's a complicated question. I'm going to punt on this one and say that it depends on exactly how you operationalize redundancy. Like if you're using something like the shared exclusions measure from Mackay and Vibral, which is what we used in the PED paper, that should distinguish between truly higher order redundancies and overlapping lower order redundancies because of the way the shared exclusion is defined. It's the information that is, you could learn by observing X1 or X2 or X3 or X4. How the O information deals with that problem, I don't know. This is the first time that question has ever been phrased or articulated, as far as I know, and so I think that's a good question. We should correlate O information against various orders of the HSX shared exclusions redundancy measure. That's a good thought. I should look into that.
That may be what I'm interpreting as a related question. It might be the same one or it might be very different. But if my interest is coarse graining networks, and so if the things that are emanating these signals that you're running these information measures on are somehow grouped together to form macro objects. A macro node, that's examining uh, some new data. Would you expect that like synergistic relationships at the micro scale when coarse grained would appear redundant?
Okay, so
There's some sort of preservation of synergy there.
So the paper that Eric and I wrote together, we tried to answer that question, and the Eric's hypothesis was that if you had a system where you could coarse grain it and improve the effectiveness, what you would be doing is you would be kind of lumping all the redundancy together and letting the sort of the unique and synergistic information shine through. Unfortunately, that was not what we found. We found that you can get all possible combinations, right? We found some systems where you coarse grain them, you get significant causal emergence, and it becomes more redundant at the macro scale than the micro scale. You may notice that Eric has never cited that paper. Like he had his big causal emergence 2.0 thing just dropped, and that paper does not get cited. We never really, I personally never felt like I understood what exactly the takeaway from that was. In theory, redundancy should be coarse grainable in a manner kind of similar to like a renormalization group sort of process. If all your neighborhoods look just like you can smooth them together. Synergy is weird because like you can't coarse grain a synergistic, like if you have 3 synergistic elements, you can't coarse grain them in a way that will like cut them in half. Like you can't assign each one to different modules, but you could coarse grain all 3 of them. And then, because then the whole just becomes the new part. So the rules for coarse graining higher order synergies, whatever they are, they're not as simple as we thought they were back in like 2020 when we wrote the paper. But that would be an interesting area of future collaboration.
There's this line of work that Narayan's supervisor and collaborators works on, which is this like similarity versus complementarity in networks. And it feels like in terms of finding a strategy for which nodes to pair up to because one of the things that I would imagine is like a huge elephant in these analyses is like how to actually do the course grading optimally. There's a lot that gets left on the table, I think, because these are just partitioning algorithms that find the V1. So I wonder if there's any way to tell with this.
Yeah, I think I mentioned this. I think we've talked about this at least peripherally. I actually think that you could use these as good coarse graining heuristics. Like I'm convinced that InfoMap is the natural tool for coarse graining, like in a causal emergence context, because it's still this idea of like compressing the system. But if you have one thing that I kind of should stress is that for all of these results, we're operating on very high dimensional probability distributions that are, either discrete or continuous, but they're not networks necessarily. Like, porting that all to a network structure is interesting, but non-trivial problem. So that's, yeah.
Can I ask a follow-up to that? Because I was actually kind of thinking the same way. Like, by the way, great talk. This is awesome.
Oh, thank you.
It's really cool. Can I just like try out an analogy and you can let me know if this makes sense or doesn't? Like redundancy would be these specific, like say there's 10 nodes. These specific 6 nodes are always up and these 4 nodes are always down or vice versa. They're always like opposite.
Yeah, they're jumping. Yeah.
That would be sort of redundancy.
Sure.
But then like you could say, okay, all configurations of these 10 nodes such that they're always 6 up and 4 down, but I haven't specified which 6 or which 4.
Yeah. Okay. Yeah, you're on the right track.
Yeah.
Yeah. So one of the go-to examples that kind of comes from the XOR gate is this question of parity, right? And so if you have 10 nodes and you assume that the parity is 0, that is to say they are the same number of ones and zeros, or the number of ones and zeros is the same versus the number of ones and zeros is different.
Yeah.
That's parity 0 versus parity 1. That is like an example of synergy because it doesn't matter which of the what the permutation is, just the parity is always preserved.
I see. Yeah, so I mean, I was just gonna sort of probe you a little more on like the interaction between that and like mesoscale structure, community structure, networks. Like, it seems to me that like a mesoscale community could have both of those sort of statistics on the states. Uh, Maybe I'm just like reading into it. But what's the what do communities in networks not get you? Yes.
So a lot of it depends on how you define your network, right? So in the case of the functional connectivity network, where you build your network out of pairwise correlations,
Yeah.
Again, more helpful to have after this with the whiteboard, but there are sort of math reasons that I sort of elided that, the three-way synergy just cannot be seen by, three Pearson correlation coefficients. Okay. That's just, again, lattice theory reasons why that is. You may be able to find a different way of building a network. Maybe if you were doing some kind of crazy Bayesian thing that was like optimizing all the posterior distribution in some way, maybe then you could get a functional network out that did represent synergies. And a lot of it has to do with what tools you use.
We jump to, there's three questions in the chat. Caroline Roman said, why does adult versus baby influence the system? I think you said that earlier.
Oh, well, adults and babies are different. Yeah, the data that I have is baby data. Maybe synergy in adulthood predicts how robust you are to getting Alzheimer's, in old age. I don't know. Somebody should do that study. That'd be really, really interesting to know. But
then there's a next one. I guess you can read it also.
Yeah. Okay. So Joe asks, great talk. Thank you, Thomas. Thank you, Joe. Is there a possibility that the brain is measured to be more redundant than what it actually is due to the way the nodes or even their groups of the brain are estimated, groups of voxels that are similarly activating? Yes, this is a really, really good question. Yes, absolutely. Every step of the fMRI pipeline is prioritizing redundancy at every moment. You have voxels, and then you coarse grain those voxels into parcels, and then you look at the Pearson correlation between the parcels. It's redundancy all the way down. So yeah, that's like a huge confound there. Is the human brain more or less redundant than other natural networks? And if so, why do you think so? My guess is that okay, I'm going to sort of channeling Mike Levin here. I don't think the human brain is like doing anything fundamentally different than really any other biological network. I think it's just doing it at scale. You have neurons that are hyper optimized for information processing. And so processes that like in a developing embryo might take place over the course of weeks or, hours can happen in the brain in milliseconds. So is the human brain more or less redundant than other natural networks? I mean, probably, but it's also just like it's more as an information processing engine, it's just more extreme. It's probably got more redundancy and more synergy just because you have more highly optimized neurons doing more stuff at a higher rate. But like, is it fundamentally different in some like cosmic Giulio Tononi sense? I doubt it.
Nice. And then Jonathan, another question.
How would you say a system's synergy dominance level changes when some nodes' edges are removed? Is it safe to say it will never increase synergy? Okay, so that's actually something that we use to significance test the O information. You compute the O information of 10 nodes, and you get a negative number. One of the things, and I got to shout out Maria Pope here because she did a lot of this during the simulated annealing paper, is finding that sometimes you got 10 nodes that are synergistic. You might be able to remove a node and actually cause the O information to become more negative, that is to say more synergy dominated, if the node you're removing is contributing redundancy to that interaction. So synergy dominance level can change in complicated and unexpected ways depending on like specifically what nodes you're removing and what the structure of the dependencies between nodes are.
You try this on single cell data or EEGs or something that's not fMRI?
Yes, so the baby data is EEG. And then I made reference to psychedelics. That was data that I recorded with John Beggs, and that was little slices of rat neurons in dishes. So And then Nick Timmey, as part of his PhD, also used similar measures, also with John Biggs and his spiking data. So synergy, whatever scale of neural data you look at, EEG, MEG, fMRI, spiking neurons, it's all there. Just the estimators that you use are different. In the neurons, you typically would use a discrete spiking estimator. In fMRI, you're going to use a Gaussian estimator. In EEG, whatever is most appropriate for a complex signal like that.
And how do you kind of build the intuition, the neuroscience intuition for this when you're looking at it from a lower like resolution, higher resolution neurons?
So the problem of building intuition, I wish I had a great answer for you. Part of what I've been doing the last couple of years is trying to do these studies like the collider study or I'm working on something else with topological data analysis, trying to sort of concretize the intuitions about synergy. I don't think we have one yet. I can tell you that synergy, again, seems to be associated with the presence of colliders. So when an element in a system is choosing its next state as a function of multiple inputs, that is a synergistic operation. That's almost inherently a synergistic operation. And so if you see synergy, you can say, hey, there's some kind of collider integrating information there. Similarly, we found with Alice Catania and Pedro Mariano that synergy dominated, again, in fMRI data, synergy dominated triads. If you look at like the topology of the point cloud, so you take those 3 time series and you project them into a 3-dimensional space, synergy is associated with like higher order topological features as well, like cavities and voids. And you can think of that as, there are constraints on what parts of the configuration space the system can visit. I don't know how great that is for intuition, but it's something.
Would you say, so for example, with some of the things that you mentioned with when synergy or redundancy is dominated, to me, because I'm from a very neuro background, so it's like trying to understand. The redundancy to me seems like something that could just arise as more strongly, not just because of the way that fMRI data, for example, is pre-processed, but the fact that there's a lot of oscillations in the brain that dictate long-term processes, like for example, hormones, right? And how they get released and they're cyclical. And that's like, because it's such a cyclical and repetitive process, that could be something that's captured as redundancy, whereas synergy could be something that's more task related. And so for babies having high synergy, it's like everything in the world is new. And so they're taking in a lot of sensory information, maybe.
Yeah, so your intuitions about sort of cyclical processes and redundancy are totally bang on the money. If you have a highly autocorrelated like cyclical process, that will typically sort of get read as inflating redundancy. Although this is a case where it really depends on what specific tools you're using to measure it. If you're using a parametric Gaussian estimator, then yes, like it's very, very easy to find lots of redundancy associated with periodic processes. If you're using one of these k-nearest neighbors estimators, the effects are different, and that depends on whether, you're assuming that it's sampled from a Gaussian versus some kind of high order point cloud modeled by a k-nearest neighbors network. And so it's complicated. That's sort of the best I've got right now. But yeah, your intuition is good.
There's no other questions. It's 3:00. So Jessica, you're talking with Thomas at teenage, so a little bit of downtime, but feel free to go and bombard the next couple of minutes if we still have burning questions. But otherwise, you'll be here the rest of the day.
Yeah.
We're chatting. There's a couple meetings. TBD on whether you'll be here next couple days, but we'll see.
Yeah, I emailed Josh or messaged Josh asking if he'll pay for my parking, depending on whether he says yes or no. Yeah.
But yeah, let's thank Thomas again. Thank you very much.
Thank you. Yeah, but, for
Takes a lot of time.
yeah, just for a one-off trip. I thought I would be here today, tomorrow, and Friday.
Yeah.
I also wanted to see Rick Bensel. But I'll be paying probably $50 to park at the Dalton Street garage today, and I can't $200 of parking just to say hi to my former PhD advisor. Like, I'll email him.
So, Greg, just one question. So, So if we consider the following scenario where, say, I have n nodes,
Mhm.
each emulating some sort of dynamical time series, let's say.
Sure.
So I have all these n choose 3 possible triangles. And I'm calculating essentially O information for all of these n choose 3 entities. And suppose the following scenario holds where the actual synergy inherent to all of these triangles are more or less the same, some constant value C. Suppose that is the case. But the redundancy, which is more or less proxied by the, say, sum of the mutual information between the three entities. So I'm guessing there is some sort of relation between the redundant information and the sum of, just say, the mutual information.
Yeah, so I sort of hear where you're going with this. I'm not sure that this is actually possible. Like, I'm not sure it's possible to, I mean, maybe with some kind of